I want to push my talk in a very different direction.
Okay.
I'm not going to speak of walkers or droplets or even mathematical functions. My concern here is to explore whether biology can help us understand better quantization. So to start with, let me say that in historical processes, transformations are collectively established over a long period. For example, the transition from feudalism to mercantile capitalism is only understood in the long term. There are different levels in the apparent continuity.
Gilles, let me
Yes,
just ask, you are not going to share a presentation?
that's right.
Okay.
I will have no PowerPoint. You have to listen.
Yeah, okay. Let's try that.
Okay. So as I was saying, technical innovations that appear at a given moment, they are like discontinuities. And we could have here a very long list of examples. Usually in history of science, we deal with things like scientific revolution or the industrial revolution. And the question is, would these changes be gradual or are they abrupt? They cause breaks and sudden cuts between the old and the new. We live in a tradition in which it's generally accepted that there are no leaps. That is, in natural history, the evolution of natural processes over time is like a continuous function. Our minds seem to resist quantization, adopting the alternative interpretation that this is a problem of scale. At the human level, we do not perceive quantization. It is interesting to note that this problem appears in every historical evaluation of events. And looking closer, it is like a historical process. It's a sequence of steps. But is this illusory? Is it mathematically idealized as a straight line formed by points? The question that I believe to be relevant is why would nature not proceed continuously in its transformations? Continuity equations have been very useful in science. They are linked to aspects of the optimization principles that have been proposed to better understand nature. On the other hand, discontinuities usually appear when analyzing changes in chemical, physical, biological, geological, cosmological domains. Quantum theory, introduced at the end of the 19th century, came to modify this conceptual framework. It began to show that nature also exhibits a quantum character. But coming now to the subject of this conference, the empty waves or pilot waves, or theta waves in the Lisbon School terminology, they have been investigated as the sources and propagators of singularities in the subquantum environment. It is important to realize that they act collectively to realize trends that are discontinuities that may manifest themselves individually, but not with the same intensity and quality of the collective behavior. Even the interior collectivities that make up bodies directly observable at our human scale demonstrate the importance of collective behavior in transition phenomena, such as freezing water, for example. Transitions are therefore not an individual issue, but a collective one, in which the whole itself transforms the phenomenon and covers it with a nonlinear action, as can be seen right historically, way back in the gravitational attraction of three bodies, which is leading to increasing complexity for a higher number of constituents. So let me say that there are examples of quantization phenomena at our human level. I think that my friend Jonathan will demonstrate the electromagnetic pendulum coupling tomorrow. This is such an example. And elsewhere, working with the Lisbon School, there was an argument developed that the universe is a non-deterministic ensemble capable of forming order and complexity. And this has historically translated into the formation of more permanent structures, chemical elements, molecules, inorganic bodies, interstellar, stellar matter, constellations, etc. So we think that this is a trend that shows that each being has a trend to continue his existence, even by transforming and creating new structures, overcoming the opposite tendency, which is disorder. Living beings emerged, organizing themselves in a collective way, which, if examined for a sufficiently long duration, will seem to be leading to a causal purpose, some degree of teleology. In the process of biological evolution, quantization was no longer forcefully attributed to gaps in the fossil record. Since saltationism evolution was proposed in the 1940s, it seems that the riddle of quantization has much to do with the problem of the appearance of forms that are favorable to perform specific functions. Or, in other words, it's the tension between morphology and physiology. Our understanding of this question also rises at other observational levels, not limited to biology. Coming back to our core of this conference, in the subquantum world, why do acrons concentrate energy while waves are in charge of its propagation? Why do crystals have the geometric structures we know? Why do atoms have their structure concentrated in nuclei, but are capable of forming assemblies in the form of chemical molecules through bonds which are outside the nucleus? We can continue such questioning, noticing once more that all transitions arising from those mentioned examples do represent discontinuities. And I think biology is particularly good for discussing these questions because evolution continues to work. It is still combining form with function. So in my talk, I want to stress how morphogenesis was examined by some 20th century biologists who thought outside the paradigm, for they were out of the box that has dominated developmental biology. So I will give a brief review of these three biologists' work, and I'll start with the classic work of Edward Russo. He detailed how natural history thinkers in the 19th century showed how function is combined with form, especially when changes in form have occurred that affected the way living beings work. This all started with the metamorphosis of plants by Goethe, who said that we try to understand things by separating them into parts. It is possible to separate a living organism into its structural elements, but we cannot recompose it or give it life back by putting the parts together. Morphology reveals that internal meaning of the constitution of an organism without approaching it in a fixed way, except as a transitory phase. The form itself is of interest only as a manifestation of the living being's internal activity. For Goethe, there is a force that carries the idea of the organism. Living beings strive to manifest this idea. They are like works of art produced by nature, he said. This conception is valid not only for an individual information, but for the whole set of living organisms, what he called the unity of plants. Sometime after that, Saint-Hilaire in France believed in a cessationist evolution and maintained that historically there was only one type of animal. And he postulated that transformations that would reduce most animals to vertebrates disregarding function compared to form. The unity of plan and composition would result from, again, a force exerted, he said, at the atomic level. Cuvier, a contemporary of Saint-Hilaire, on the contrary, he was adept of teleological transformation in which function would take precedence of form. An evolutionary theory of the type defended by the previous thinker Saint-Hilaire is similar to the proposal that Charles Darwin would later make, assuming that a variation occurs randomly and not as a direct response to environmental changes. For Saint-Hilaire, form determines function, adapting existing material to meet new demands. But for Cuvier, it is function that determines form and creates new organs in response to new functional needs. The leading English biologist, Richard Owen, in the second half of the 19th century, believed that organic forms result from the action of two antagonistic principles. One of them would be responsible for the repetition of structures and unity of organization, and would produce structures such as the skeleton, the pentagonal symmetry of the echinoderms, or the crystalline spicules of sponges, in the same way as the repetition of crystal forms occur in the inorganic world. The other principle is of a teleological nature and would respond for the function of living beings in an adaptive way, capable of producing a diversity of organic beings. Von der, the German embryologist, came to the conclusion that a kind of creative thinking in cosmic space brought together scattered masses in the form of spheres all over the cosmos. The same happening that created life forms from the beginning out of dust on the surface of metallic planets. For him, evolution took place also in a cessationism way, not by random or continuous variations, but as a result of this general principle of creative organization. According to him, the purpose of life is part of the purpose of the entire universe, The German Schwann, he put up the theory of the organism that he opposed the teleological vision of a vital force. He said that he was a materialist and there are only blind forces in nature. And at that time, atomist materialists saw each isolated living cell as a vital and independent unit. That is, cell morphology left physiology in the background. It should be remembered that the complexity of beings was responsible for the new organs and new faculties. And this was the theory of Lamarck early in the 19th century, which goes also in the direction taken by Cuvier and postulates an active self-adaptation by the organism. For Lamarck, as for Owen later, there are also two forces at work which are responsible for the variability of beings. One he called the vital force that tends to produce an increase in complexity, and the other called by him as circumstance, which is equivalent to the environment, tends to disturb and diversify this increase. The problem is to correlate the causes of changes in form along those in function. How do the parts coordinate to form the whole and guarantee the essential condition of survival? So this is a completely parallel problem to what we face with waves and particles. In the second half of the 19th century, teleology was considered to have been banned by the evolutionary theory of Charles Darwin, who said that adaptations are random. Only relatively few biologists dared to contradict Darwin and continued to advocate a genetically functional, that is, a causal morphology in which the evolution of form could not be isolated from the evolution of function. The German Wilhelm Crookes tried to compromise between purely mechanistic materialism and metaphysical vitalism, but he ended up adopting Lamarck's idea that external stimuli can produce new structures that over many generations end up becoming hereditary, even in the absence of new stimuli. Darwinian natural selection cannot explain the origin of a functional structure and the functional harmony of the structure, as thousands of cells would have to vary together at the same time so that some real advantage could arise in the struggle for survival, which is highly improbable in individual selection. By studying the properties of blood vessels, Crookes concluded that they have to be intertwined with the function of different tissues and organs. Form is not something fixed. It is an always dynamic manifestation of functional activity capable of responding to foreseen and unforeseen contingency. Function creates the organic need, and only after many generations does the organ appear before the function is actually performed. The differentiation of tissues in the embryo would be due in large part to a qualitative division of the cytoplasm and not the nucleus of the cells. Samuel Butler postulated that living beings are active, intelligent agents, continuing what their ancestors already did and suffered through an intense but unconscious memory, which acts until it becomes an automated memory. Variations become hereditary in the way of a psychological process, with the nature as memory. We are more unconscious and have less control over our circulation and digestion processes, which are extremely ancient functions. linked even to our invertebrate ancestry. Who would be the designer of this intelligent design? For man, it is man himself, according to Butler, not individually, but man in his entire existence beyond the species, that is, from the dawn of life to the present moment. Butler's proposal would possibly satisfy those who subscribe to a monistic interpretation like Leibniz, or a panpsychic one like Spinoza. In this way, all things that exist would be animate, regardless of whether they are alive or not, albeit in different degrees. This is the path opened by Cuvier and von Baer at the beginning of the 19th century and followed by scientists even in the 20th century. For example, Hans Driesch, the German who did not hesitate to get rid of Darwinian evolutionary dogmatism and accept vitalism and teleology in the footsteps of the classic view of Aristotle. Organisms could automatically repeat inherited functions, but they could also create new functions in response to new needs when facing environmental adversities. Ontogeny would not then be a recapitulation of phylogeny, because the universe is not deterministic. It should be taken into account, however, that there is a similarity between the laws that govern evolution, so that similar responses occur even without following a deterministic way. Evolution could therefore have started over again many times and from very different primordial cells, such the character of saltationism might prevail in evolutionary development rather than continuity. A second classic work is that of Dorsey Thompson. He worked on symmetries and mathematical proportions of living beings. He highlighted that Immanuel Kant already expressed that the living organism is already his telos, or the final cause of its own generation and development process, thus playing the role of both an architect and a builder. The embryo, in particular, is reaffirmed by Hans Driesch with his concept of entelechy for the living being, assumes a strongly vitalist epigenetic causality and intentionality. Mechanism and teleology are intertwined. D'Alembert, for that matter, the mechanists in general, deny that there are final causes. The evolution, as narrated by Charles Darwin in the Origin of the Species, is, according to Dorsey Thompson, disappointing because he failed to list the branches of the tree of life. For Darwin, there would be infinitely small continuous variations only. Why are there then so many gaps in continuity? A barrier has to be crossed to move from family to family, without which there is no longer the possibility of direct comparisons between them. How do birds descend from reptiles, mammals from quadrupeds, or in turn quadrupeds from fish, invertebrate vertebrates, and mollusks from coelenterids, or even one group of protozoa from another. And now I come to the third author, which he was a biophysicist, George Wagensberg, a Spaniard, who analyzed this question of evolution from a very original point of view, turning to the forms that are preferred by nature. Nature would have solved this problem on various scales through 9 fundamental forms, following a typology of functions applicable to living beings, but also to non-living beings. The first shape is that of the circle. The circle connects to the functions of generation, rotation, defense, and minimal energy dissipation. Associated with this, the sphere protects and envelops the maximum volume for a minimum surface. being suitable for beings relatively fixed in space. Examples of application in this way are a variety of fruit, eyes, eggs, and everything that enables the isotropic growth of microorganisms on rounded corners in successive layers. The circumference can deform into an ellipse due to the superposition of an aerodynamic function, as in the cross-section of fish, or turn into cylinders or cones, such as in trees. A second very common form is the hexagon, which has the function of compact paving, or as for example the honeycomb, which is made of hexagonal cylinders, saving wax and space. Other examples of this form are tortoise shells, insect eyes, and if the available space is not flat, the best paving is achieved with pentagons surrounded by 5 hexagons, as in the soccer ball. The third identified form is a quite common one, is that of the segment. The function of the segment has been to locate or connect elements, enabling displacements of the beam or its extensions, also serving as a measurement standard in the resistance element, as for example in the web of spiders. Associated with the segment, a fourth form would be the angle, that can be visualized as a bending of the segment around the vertex, with the function of pointing, gathering, concentrating, and penetrating. Examples are the spines of plants, the teeth of sharks, or the ribs in relation to the spine. A fifth form would be the spiral, which allows the function of dense packing, as in the tails of various animals, such as the chameleon and the seahorse, or in the rolled snouts of insects such as the moth. Another associated function is of growth, maintaining an original space-saving shape, which occurs very commonly with seashells. What could be a spatial transformation of the spiral is considered a sixth form, is that of the helix, which has the additional function of gripping and also of compacting or intensifying the grip, as in the coil tail of various monkeys or in the DNA packaging. The parabola is the seventh form. It serves to emit, receive, concentrate on a focus. And one good example was the bat's spatial sensing system within the parabola-shaped auditory organ of bats. An eighth fundamental form is that of the wave, whose function is to displace, diffuse, communicate. For example, fish and reptiles move by producing transverse waves with the body. More generally, the wave makes it possible to move information without displacing matter. And finally, a ninth form would be the fractal, which is capable of filling, subdividing, and colonizing a given space. Examples of fractal elements are much varied: atmospheric rays, cauliflower, fern leaves, branches, the circulatory system of vessels in animals and plants, neurons, and so forth. So I come to my final considerations. The evidences in favor of evolution support the idea that evolutionary transformation does not appear to have been continuous. The great taxonomic divisions of macroevolution, the phyla, do not seem to have been constituted out of a continuous and uninterrupted differentiation of species, but would rather have erupted in a quantum manner in a relatively short time. And morphogenesis seems to be linked to the non-linearity of evolution. In other words, form and function are manifestations of the tendency to increasing complexity and harmony, which unifies and gives a certain sense of, paradoxically speaking, continuity, even if they are materialized by discontinuities. And the natural unity of the organic and the inorganic world can be appreciated by the convergences in both cases of the rhythmic tendency, which was glimpsed in the case of quantum theory by José Croca, and he gave a speech on Tuesday about the rhythmic thought in quantum theory. So I think that any activity that we think that relates to humans cannot be imagined in out of this unitary context. And this trend to exist with increasing complexity and harmony is what we could approximate at first unsuspected worlds like quantum and the whole cosmos. And I thank you for your attention.